Okay. Hi, everyone. I think I'm the first distance student to lead the discussions in Psych 562 for this semester. So thanks for having me. Thanks for listening to the presentation. Dr. Barton gave me the option of doing it this way and recording a presentation rather than lead the discussion live. The main reason that this works best for me is because I currently live in Abu Dhabi in the Middle East, and it's about a 10-hour time difference. So we're 10 hours ahead of you guys there. So I would have to stay up quite late in order to be involved live in the discussion, which would have been my preference, but I think it just makes more logistical and practical sense this way. So this week I'll be talking a bit about the virtual environments and motion sickness. And I guess before I get going on things, I'll just give you guys a brief introduction on who I am. So as I said before, I'm living in the Middle East. I'm from Canada originally. I did my undergrad at University of Waterloo in the kinesiology program there, and then streamed into ergonomics, and got a job working in the nuclear industry in Ontario at one of the nuclear utilities there as a human factors specialist. And primarily I was involved with design of human system interfaces, worked on some control room design work. Later in my career there, did some work on the organizational side, and then the opportunity to move here and work for the newly formed nuclear regulatory body came up. So I've been here since 2011, again working as a human factors specialist. And the situation in the Middle East, in the UAE, is that they are building 4 nuclear reactors, and they need people from around the world who have some experience in nuclear and specialization in different disciplines, one of them being human factors. So that's why I'm here, and I've been here for, I guess, roughly 2.5 years, and so far so good. So that's a little bit about myself, and I guess I'll get going here on the presentation. So today we'll talk about these 2 articles, the Marin and Glavin article and the Stanley et al. Article. And both of these articles, the primary topic is on virtual environments, the use of virtual environments, and some issues. Wednesday we'll address a bit more of virtual environments with the Vora et al. Paper, which is a research paper on a specific application of VE, and then get into the talk on motion sickness, which will keep us busy for the rest of Wednesday, and then also, I think, most of the day, if not all of the day, on Friday. So before I get going on the papers specifically, I thought I'd talk a little bit, give a very brief overview of the history of virtual environments. And I actually put some of these slides together, I think it was in Psych 561. So I didn't go to too much trouble to find all this stuff out. I just looked at my my files from my history and pulled this stuff out. So in 1956, a guy named Morton Heilig developed this thing called the sensorama. And he was pretty curious and I think pretty keen on developing something that would give people this multi-sensory virtual experience. And from the pictures you can tell this thing looks a lot like a video game, an arcade machine. What this thing did was it projected film, and it had audio that had been pre-recorded. It also had vibration, wind, it had odors, and all of this stuff was designed to make the user feel like he or she were actually in the film rather than simply just sitting there watching it. So this is very similar to today's movie theater experience where we have 3D, but I think there's some theaters now, I know in the UAE we have theaters that are 4D, where you get the experience of the 3D environment, plus you have odors, plus your seat moves around, plus you can even get sprayed in the face with water, I think. There's an option to have that happen. So things have greatly developed, but this guy, Morton Heilig, was kind of the pioneer in developing this type of technology. He also, in the 60s, came up with a prototype, or at least a patent, for the first head-mounted display. And these guys, Sutherland and Sproul, further developed the HMD technology and called it the ultimate display. And this was the first head-mounted display that actually used computer-generated images. And it also was the first stereoscopic display, so you had different images going into each eye. So this was a fairly hefty technological advancement at that stage. This used a mechanical tracking type device, and as I said before, it used the computer-generated images, which was different because a lot of the earlier ones used this pre-recorded video. So the computer stuff, although it was rather crude and didn't provide much detail, certainly led us to a lot of the technology that we have today in head-mounted displays. So another example of the development, and this is, I guess, less in the area of head-mounted displays, but more looking at virtual environments where, like simulators, driving simulators, flight simulators, those types of things. This Aspen movie map was maybe the first of its kind in that regard. And what these guys basically did from MIT was that they went out to Aspen, Colorado, and they drove around and they filmed the drive using numerous cameras from numerous different perspectives. And then they gave the user the ability to basically navigate through Aspen using this interface, and they could control the interface. So they could control the speed with which they moved. They could also control the direction that they moved. They could even choose to stop somewhere, say at a bakery or a shop, and go inside, provided that had been pre-recorded. So this was probably the first true hypermedia experience that was developed. And just on the bottom there, the term virtual reality was coined by a guy named Jaron Lanier in the 1980s. And that's basically for trivia, nothing else. Now. Okay, so we'll start talking a bit about the Marin and Glavin paper now. So the overall general topic of this paper is simulation in medical clinical settings. And a couple of the high-level issues that the paper addresses are the need for simulation training to meet the high demand for more medical students and practitioners these days. Additionally, simulation doesn't replace the clinical experience, but it can certainly enhance it. So this paper looks primarily at the uses of simulation for education within the medical industry. And it talks about a few processes, educational processes that underpin simulator training. And I would say that these are not specific to the medical world. These are things that would be specific or would be applicable to other domains as well, but are probably specific to simulator training. So the first is deliberate practice. So deliberate practice basically means that the skill must be practiced with clear objectives, an appropriate form of simulation, and an initial demonstration. So it's also important that the demonstration makes clear the differences between the performance of the task using the simulator and the performance of the tasks in the real world, because it's important to avoid this negative transfer of skill from the simulator to the real world if you don't make this distinction up front. The second underpinning is reflection, and Marin and Glavin talk about reflection as an active process that helps the learner to link new information and experiences with previous knowledge and understanding. So this is basically building and reinforcing neural pathways. And feedback needs to happen throughout this whole process, the whole educational process, and use of the simulation. And this helps to ensure a positive transfer from the simulator to the real world and enhance learning. The second bullet here, the agreement of performance standards, may be a benefit to assessors. I think here, and this is also true in the nuclear industry, that when you're going to assess somebody using a simulator, it would be important, and it is important from the assessor's perspective, to have some kind of a standardization of what these standards or what these assessment performance measures are. Ultimately, the main aim is the successful transfer of learning from the simulator to the clinical setting. So from the paper, they talk a bit about advantages of simulators. And there's obviously drawbacks as well, and we'll probably touch on those as the presentation goes on. But some advantages, and these are directly from the article. First being that the risks to patients and learners are avoided when you compare this to, say, doing the same type of a task in a real-world environment. And this is quite obvious, especially when it comes to the medical field. Undesired interference is reduced. Tasks or scenarios can be created on demand. This is something that's quite important. I know that when they use nuclear simulators for training of nuclear operators, if a scenario doesn't go as planned or they feel like they need additional training under a certain scenario, the instructor can basically enter into a scenario or modify a scenario when it's needed, when they deem it's necessary. So this is obviously also a benefit within the medical practice. Skills can be practiced repeatedly, so obviously this is a very advantageous thing. And training can be tailored to individuals. So this basically means you can tailor it to the specific job or function that the person has to perform in that setting. Retention and accuracy are increased. There's a transfer of training from the classroom to real situations, and that's enhanced. And standards against which to evaluate performance and diagnose educational needs are also enhanced. Now we'll address the issue of fidelity. So within this article, they talk about two types of fidelity. There's the physical or engineering fidelity and psychological fidelity of the simulator. They make the point that the psychological fidelity is more important, and they address this through saying that the high engineering fidelity is not necessarily required for successful psychological fidelity. So skills can be learned with limited engineering fidelity. So when we talk about engineering or physical fidelity, we're basically talking about the degree to which the physical characteristics of the simulator match the real world. Psychological fidelity is the degree to which the skills required in the real task are captured in the simulation. So a potential discussion point, and you'll see throughout my presentation I've put these potential or possible discussion points in italics. Under this topic, what applications where we would need high levels of both physical and psychological fidelity. And it's something you could either maybe discuss now within the group or leave till the end. So the next thing we'll talk about is the different types of simulators that are currently used in medical education, and I'm sure elsewhere as well. The first kind are part task simulators. So these only replicate a part of the physical environment, or also a part of the task or skill that needs to be trained on. The next are computer-based systems. So these use information to make decisions on treatment within the medical industry. Virtual reality and haptic systems. The use of haptic systems is very important in training surgeons, and this provides the haptic aspect of the simulation provides some resistance or the touch and feel. And as you probably can imagine, surgeons, and I think all of us who would be lying on a table being acted on by a surgeon at some point in our lives would think, had that surgeon been trained using some type of a haptic system, we'd feel more confident that they would be able to replicate that task that they perform in the simulator in the real world. The medical industry uses virtual patients, and I've never seen one of these, but they sound pretty interesting. So it's basically like a lifelike doll that has vital signs, and they use it in certain simulator scenarios. The next thing is a simulated environment. So these are basically going from kind of lower level simulation to more higher level integrated simulation. And a simulated environment, you could actually have a hospital ward. So in addition to just simulating, say, your interaction with a patient, you could simulate your interaction with a patient in a room where you have other people doing what they would normally be doing outside of that room in the hospital ward to give you a more lifelike experience. And this is kind of, I guess, what an integrated simulator would be. So we have a mannequin or this doll patient driven by software, and these things can simulate the effects of drugs. And as I said before, if you put these in a realistic or a simulated environment, this adds to the psychological fidelity, whereby the skills that are actually being simulated are more likely to transfer into their application in the real world. These integrated simulators, though, are very complicated and cost a lot of money. So you can assume that the companies are probably reluctant to use them unless absolutely necessary. If they can get away with other forms of simulation in their training that are just as effective, why would you go to the expense of doing something full-blown? So another potential discussion point, and this goes across the board when you're using simulated environments. How would you create stress in a simulation? This is a bit of an issue. And as we all know, lack of stress can lead to underperformance, so we have this adrenaline gap. Too much stress can also lead to a problem with performance. You know, with the Yerkes-Dodson U-curve, we all know that there's like this optimum level of arousal that can lead to optimal performance. So you're understressed or overstressed, you could have some issues. So how could we potentially address this problem in simulated environments? The next thing we'll talk about is assessment using simulators. So in simulators, it's best, Marin and Glavin make the point, it's probably best to use summative assessments. And these are things that look at, basic psychomotor and communication skills, but typically you're looking at what's the end outcome of a task. Was the task performed successfully? You can break it down into these specific lower level measures, but the overall outcome of the task or the performance of that skill is what's most important. When it comes to non-technical skills and measurement or assessment of non-technical skills like communication, it's been shown that there's some issues with the validity and reliability of the scoring systems used to assess these things. And I know from my experience in nuclear, this is also the case. When you have a crew of operators who are in a simulator and they're being assessed and they're actually acting or operating within this environment under an accident scenario, being assessed by experts. Do they use three-way communication? Do they independently verify and validate actions of other operators? Are they following procedures? These types of things are difficult to measure objectively. These are things that you usually have an expert in there overseeing and making a judgment on whether they were done correctly or successfully or not. And it sounds like it's the same case when it comes to the medical industry. They make point that there's vast differences between airplane and patient simulators. And this is especially true with the fidelity of the simulation. In airplane simulation, there's a high level of software modeling, and the response of patients is quite a bit different than the response of an aircraft. Well, that makes complete sense. They make the case that pilot or aviation simulators are set up such that if a pilot can show that they can successfully fly a plane in the simulator, there's pretty high confidence that he can actually fly the real plane. And I can see that point, but I guess by making that point, they're saying that if a doctor or surgeon shows that they could successfully perform a task in a medical simulator, they don't feel as confident or comfortable saying that they're sure that task or skill could be performed in the real world. And this may just be a limitation of the application of simulation to the medical profession. So some of the conclusions from this article, are one in particular, are that you must be careful not to allow technology to drive education, but rather allow technology to supplement it. And I think this is important, and we'll get into this when we talk about the next article as well. So maybe I'll save that discussion for then. So moving on to the Stanny et al. Article. The main topic that they address here is human factors issues in virtual environments. They also talk about health and safety issues and social implications, but because we're human factors researchers or practitioners, I will focus most of this discussion on the human factors issues. So, human performance efficiency in virtual environments. One quote from the article, which I thought was rather poignant: the goal is to build virtual environments that minimize learning required to operate within them, but maximize the information yield. There's quite a bit of discussion within this article about minimizing the learning required to operate a virtual environment. And it talks about ways in which you can do this if you're designing a virtual environment. So ultimately, you don't want to design a virtual environment that requires an excess of cognitive resources to navigate within it, or act within it, or to perform within it, such that you're detracting from the ability of the person to learn. They also make the point that a systematic approach is required in developing VEs, rather than, say, an ad hoc trial and error type approach. They say this will lead to more efficient and effective development. I tend to agree. I mean, when you apply a systematic approach to most things, you're more likely to guarantee the best outcome than if you just use trial and error. And I think it's a more efficient way to deal with this issue as well. Apologies for this slide. It's kind of blurry, but I took it right out of the article, and it looked much better when it was in the PDF. So I'll just go through these quickly. This is, again, directly from the article. And these are human factors considerations for virtual environments. So let's start at the top left. First question is, will the user get sick or be adversely affected by VE exposure? We'll talk a little bit about some of the health and safety issues associated with VEs. And later this week, we'll talk quite extensively about cyber sickness and motion sickness. Which tasks are most suitable for users to perform in VEs? So this is kind of going back to the previous article too, talking about you don't let the technology drive the way that you're going to use it in education. You should basically be looking at this from a top-down systematic approach to training perspective, where you identify the tasks or skills that maybe best lend themselves to the use of virtual environments. Which user characteristics will influence VE performance? We'll talk a bit about this later. Will there be any negative social impacts? We'll talk very briefly about that near the end of the presentation. How should virtual environment technology be improved to better meet the user's needs? I mean, this is a big question, and this is probably will be the focal point of the next few minutes. And how much sensory feedback from systems can the user process? Will the user perceive system limitations? And what types of design metaphors will enhance the user's performance? So we'll address most of these in the next couple minutes. So again, talking about human performance efficiency. So what measures could we use to assess human performance? And Stanny et al. Make the case we should focus on task outcomes. So this is similar to what I spoke about before. Rather than maybe break down things to a fairly small or less complex level, we would rather look at the outcome of the task. Was it successful or not successful? I think that there's a case to be made that it's important to look at other measures or other human performance attributes when you're looking at the use of virtual environments. And we can talk about that in a little bit. One thing that's a specific issue in virtual environments when it comes to human factors is navigation. So good navigation or well-designed navigation is necessary for efficient human performance. This can detract from performance if it's not well designed. So it might be best if we thought about developing standards for navigation within virtual environments that would enable users to maintain spatial awareness. This would then lend itself or mean that we could measure the navigational complexity of a virtual environment. So I compare this a little bit to if we're using, say, a subjective workload assessment methodology like the NASA TLX. There's no specific red line to say that's too much workload or too little workload. It's meant to be more or less a comparison. So you say we do a task this way or we do it this way, which results in a better workload profile. So I think the same could be applied here for navigational complexity. We could have a measure that would be used for comparison of different virtual environments rather than saying this environment is the best, or saying that there's a red line when it comes to the complexity of navigation within a virtual environment. That might not be attainable. Presence is a big issue when it comes to virtual environments. And I think we'll be talking about this a little bit more as the week goes on. So what presence is it's a function of vividness and the level of interaction of an experience. There's a question about whether high presence equals better performance in virtual environments. And the article makes the case that there hasn't been much evidence to demonstrate this. One of the reasons that this may be the case is that we don't have quote-unquote solid measures of human performance. This could be a potential discussion point later for you guys. I think in addition to human performance measures, there's also a need for better measures of virtual environment performance. Going back a little bit to the last slide, talking about the navigational complexity. That would be one example anyways. Task characteristics of virtual environments. So I talked about this briefly before. How suitable is a task to virtual environments? Don't let the technology dictate where it should be used. Let the task and the applicability of virtual environments to that task dictate where the technology should be used. So when applied to relevant tasks, virtual environments can enhance the transfer of training, which is obviously very important. And you have a higher level of interactivity, which is beneficial, but this interactivity within the virtual environment shouldn't interfere with information processing limitations. And in addition to this, the level of immersion that a person experiences, the benefits of that when it comes to their performance are quite a bit less empirically supported than those of the level of interactivity. User characteristics. Again, this is something we need to consider. It's been shown that individual differences do have an effect on both the level of presence and cyber sickness. We'll talk a bit more about cyber sickness later this week. If you're an expert or novice user, your ability in spatial memory space and awareness, even personality differences, age obviously can play a role because your perceptual capabilities decline, especially with vision and also with hearing as you age. So here's another discussion point. Are there difficulties in applying the user-centered design approach to virtual environments because of these specific influences of user characteristics on virtual environments? So just something to consider, and it may not be any different than when you design any other type of interface, but maybe there are some things specific to virtual environments where it would be especially difficult to apply the user-centered design approach. So other areas that we need to consider with human performance in virtual environments. Sensory limitations of humans, including both visual perception, so perception of motion, optical flow, visual field, which can be majorly affected when you have a head-mounted display on, stereopsis, binocular vision, and also binocular rivalry. Audio perception. This is key for the localization of audio through both intensity and temporal differences. And I'm sure that any of you who took PSYC 444 are quite aware of both visual perception and audio perception issues and how they may relate to virtual environment design. A few others. So in addition to auditory and visual sensory limitations, what about physiological or haptic and kinesthetic perception? So as we know, force, pressure, adaptation, and the lack of understanding of kinesthetic factors, which is your awareness of your body in space, can make it difficult to design virtual environments to be realistic when it comes to these factors. Multimodal interaction. So you can design a virtual environment to be rather complex and to involve different modes of both input and output or feedback. Now these could be beneficial, but again, it's one of those things where it could also not be applicable or not be the right thing to do in some scenarios. So again, something to consider where this may be useful. And the other thing that they touch on, the use of design metaphors in virtual environments, kind of like affordances, the concept of affordances. Developing these metaphors can help improve user performance and understanding of the environment. And these could also maybe be used when we develop design guidelines for virtual environments, which as a HF designer, which some of you may be now or at some point in your career, you would find to be very useful and very beneficial. Health and safety issues. So we're just about to finish up here. Microscopic effects. So what are the health and safety implications on the eyes or EMF exposure, the auditory system if you have a very loud type of virtual environment? Overuse injuries. Now I would expect that these types of things would only really come into play if you have a person who's exposed to a virtual environment for a long period of time or very, very frequently. And macroscopic effects, trips, falls, cyber sickness. We'll talk a little bit more about these types of things as the week goes on. Social impacts. This is an area that's not currently well understood, or at least that's what the paper said. But there may be some research that's been done in recent years that has helped to improve our understanding. When I talk about the social impacts, this is the misuse or abuse of virtual environments. Can they lead to violent behavior? I know there's been a lot of discussion about these first-person type video games where you're shooting people, mind you, in a gaming virtual type environment. But does that lead to the potential for more violent behavior in the real world? I'm not sure. That's not really my area of expertise, but you certainly read the newspapers, especially when we have these shootings, and some people want to make that connection. Traumatization may also be something. If they have a bad experience in a virtual environment, will that then traumatize somebody in the real world when they encounter that experience again? So here's the last discussion point that I'll bring up. Do HF practitioners have a direct role in considering the potential social implications of virtual environments? It's not necessarily something that we are, I would say, well versed in. So is this something that we need to consider, or is this something that other disciplines need to consider that we need to include as stakeholders when designing virtual environments? So just to summarize some of the potential discussion points before I sign out for today, and these are just the ones that I included in the previous slides. In what applications might high levels of both engineering and psychological simulator fidelity be needed? How do you create stress in simulation? What would constitute more solid measures of human performance that could be used to assess virtual environments? Are there difficulties in applying the user-centered design approach to virtual environments? And do HF practitioners have a direct role in considering the potential social implications of virtual environments? So I think I've probably exceeded my allotted time, and I want to give you guys some time to discuss, since that's supposed to be my role, is just to be a discussion leader, not to hoard the discussion. So hopefully this has been useful, and sorry that I'm not there live, but yeah, hope that you enjoyed it and maybe learned something, and it facilitates a good discussion within the group. I'll talk to you guys again on Wednesday. Thanks very much.